Program Director, Professor Petrocioni, colleagues from Dubna and local. First of all, allow me please to express my gratitude to the organizers for their kind invitation. I wish just to share with you some of the work which was carried out partially at Dubna with colleagues from Dubna, more precisely at the Frank Neutron Laboratory, and on which we have continued since 1993, non-stop up to now. It's related to neutron optics. And how can I say? It's at the interface between condensed matter, neutron physics, astrophysics, as well as cosmology, as you will see. Sorry. Well, neutron optics is of interest specifically because the neutron is sensitive to the four forces, and it is a really a master component or pivotal component of the standard model, as you will see. And of course, from quantum mechanics point of view, cold neutrons specifically are of a special interest because the wave particle duality, and therefore it's an ideal quantum mechanic tool. Just to mention that in effect, the quantum entangling or the entanglement phenomena was proposed by Helmut Rauch and Anton Zeilinger as early as the 60s, and that was focusing on neutrons in particular and cold neutrons. Well, colleagues, the work that we have that I will be presenting to you was indirectly initiated at the Frank Neutron Laboratory in Dubna in 1990s, 93 approximately, and since then we have not stopped more or less. Yet indeed, for the moment, there is a limitation in terms of the cold neutron source that is required. The neutron, the type of neutron that we are looking for or that we want to use, but nonetheless, the neutron reflectometry at Dubna at the FLNP is an ideal to pave a way to the basic experiment of a neutron reflectometry or neutron optics in general, and then embark with our colleagues from Dubna and from Kurchatov, from other from other institutions in Russia, to embark together in more or less using the cold neutron source in other parts of the world. And specifically the ESS, the European Spallation Source in Lund in Sweden. Why, colleagues, it's extremely important, the study that I'm presenting to you, because it's related to the lifetime of a neutron. As you are aware, a neutron, a free neutron has a limited lifetime, about 14 and some tenths of seconds, and upon its decay, the neutron consisting of 2 down quarks and 1 up quark decays to a proton, through which is 2 up quarks and 1 down quark, and an antineutrino as well as an electron through a bosonic relaxation somehow. Colleagues, the death of a neutron somehow, or the decay of the neutron, is extremely and paramountly related to the early stage of the creation of the elements, and in particular it is related to the light elements, hydrogen, helium, and others. And the ratio of neutron of protons relative to or protons relative to neutrons is extremely linked to the decay of the neutron, and that is why the standard model is heavily bound to the lifetime of the neutron. And simply said, for a physical chemist or how can I say, any person related to condensed matter would state simply said that a death of a neutron is the birth of the Mendeleev table somehow. And of course, colleagues, the standard model and the cosmology model more or less is more or less related to this early stage of the creation of the neutron and the proton ratio. And colleagues, I would like just to point out to this limit here of a 10 to minus 6 seconds between 10 to minus 6 and 10 to minus 32 at the early stage of the birth of the universe, and it's here more or less in this range that the precision of the decay of the neutron is required, so to confirm or infirm the standard model as much as the lifetime of the neutron is concerned. And colleagues, the decay of the neutron is paramount when it comes to the nuclear chart, whereby the nuclear chart is governed by the blue section, as you can see, as well as the orange section, which are related to the beta decay. So the decay of the neutron, its a neutron lifetime, is a paramount again, colleagues. Well, as I mentioned, colleagues, the ones that we are speaking about are free neutrons who by decaying give a birth to a proton, an electron, and an antineutrino, and of course to light elements, hydrogen, helium, and others. Feynman diagram wise, that is more or less the configuration. And unfortunately, up to now, colleagues, the precision of on the neutron lifetime was and is limited by the two major standard techniques, that is the beam technique and the bottle technique, where the precision is a plus minus 6 and plus minus 0, plus minus 2 seconds and plus minus 0.6 seconds for the technique, the bottle and the beam respectively. Here in colleagues, what we have proposed, which was accepted by the neutron community as a whole, is the usage of cold neutrons and trapping them in a Fabry-Perot resonator. By trapping these Fabry-Perot resonators, it is possible to have a high precision on the trapping time, and therefore possibly to have a higher precision on the neutron lifetime, on the lifetime of the neutron. And for such a colleagues, I will not go through this, but I will certainly revert back to this diagram here, whereby it involves the total reflection of the neutron by Enrico Fermi, and of course the wave particles duality of de Broglie, and certainly more or less base ourselves on the width at half maximum of these tunneling resonances, and use the Heisenberg uncertainty more or less to appreciate the precision on the lifetime, or the life trapping, sorry. Then I will go to the second case, whereby we will be using not only one Fabry-Perot resonator, but a multiple set of Fabry-Perot resonators, and how can I say, using the same process to show this tunneling effect of a neutron wave particles is a paramount in this kind of studies. Colleagues, these results that I am sharing with you have been published just recently in this year in Journal of Neutron Research, and in effect this work, which was published just this year, 2023, is in effect it's a follow-up of a large amount of investigation carried out partly in Russia, partially in France at the Laboratoire Léon Brillouin, Réacteur Orphée, in Dubna at the Bansk Berliner Neutron Scattering Zentrum, as well as the Atom Institute this work. It was Dmitry, late Dima Korneyev, and late Leonid Chernenko from Dubna. Colleagues, it was a series of a number of publications in that regard. I will not go through all of them. I'll just mention to you that in effect, this work of trapping neutrons, it was not a once-off work, but quite a marathon type study. So at the end, we have managed to identify the ideal structure using quite advanced optical calculations, quantum mechanics, and we found out that if we take a Fabry-Perot resonator, a thin film Fabry-Perot resonator consisting of two highly reflecting materials of such as nickel or isotopic nickel 58, separated by titanium, thin layer of 1,000 angstroms, while the thickness of the reflecting material is 100 angstroms. Then in some configuration whereby the angle of the neutron beam is less than 1 degree, and therefore requires a high collimated beam coming from the neutron reactor via the neutron guides. And then if it is the case in some resonance conditions, obeying to the tunneling phenomena, so the neutron wave packet, the cold neutron wave packet, will not be totally reflected. Yet under total reflection condition, it will not totally reflected. It will tunnel through the first reflecting barrier, and then go through the second barrier also and be transmitted. And in between the neutron wave packet, which would have tunneled through the first reflector, will be trapped somehow, and it will have some resonances, resonant wave packets trapped in the Fabry-Perot nanoresonator. And in that regard, we will be observed, those who have tunneled would be able to be detected in the transmitted beam, and therefore, of course, they will be detected also indirectly in the reflected beam as a dip in the total reflection plateau and in a maximum in the transmission. And colleagues, that trapping or somehow is related to the neutron lifetime, and the neutron lifetime, colleagues, is a pillar component of the standard model. How? The standard model is governed by the Kobayashi-Maskawa matrix, whereby the bulk of the elements of the matrix have been determined with a high precision, except this one. And this is the one which is really nagging the cosmology and the standard model community. That first element, in effect, is related within this equation, and all of them are equal to this one there, and therefore we need to have high precision on this, and therefore we need to have a high precision in particular on this one. And this one, unfortunately, is dependent of the time life of the neutron. So therefore, it is necessary to have to determine the time life of the neutron with high precision, to have this element with the most higher precision, and therefore to ensure that the Kobayashi-Maskawa matrix elements, all of them are with high precision, and therefore to confirm the standard model. Unfortunately, colleagues, there are two major techniques which were used so far. That is the beam method and the bottle method. The beam method is mainly by the Canadian and the US, while the bottle method is mainly by the European and the Russian Federation scientists. As you can see, colleagues, since it's in the inception of this idea of measuring the neutron lifetime by Norman Ramsey, it happened that these two techniques, they give always two different values, and these two different values, the difference between them is around 10 seconds, and these 10 seconds persisted within the years, non-stop. you would, in addition to that, colleagues, the bar error on the time life seems decreasing within the years due to the advanced detection technologies that we are using both in the two techniques, even including the bottle method with Seremyatnikov and his colleagues and other colleagues from the ESS and the ELL have managed to get a low bar, but still, colleagues, as you can see, the time life measured by the beam time is 888 plus minus 2 seconds, while the bottle one is 879. That is a difference of course, 10 seconds still, but the precision is plus minus 0.6 seconds. And I would like colleagues to point out that with the method that we are proposing, the precision is plus minus a picosecond, as you will see. The neutron that we are interested in are cold neutrons, which are really very, very slow neutrons, and therefore their wave packet nature, quantum mechanic behavior is adamantly present, and they are the ones who can be trapped easily or manipulated optically. And of course, colleagues, I will not, due to limitation of time, I don't want to go through the details here, but just to show you that the work that we have, we embarked in is in effect based on the total reflection by Fermi, but the polarization by Arsène Gukasov, and quite a number of other phenomena which were observed within the years. So colleagues simply said, in our case, we will take a Fabry-Perot nanoresonator consisting of two highly reflecting thin films of 100 angstrom thickness, that is nickel, separated, two nickel layers separated by a thin film of titanium of 1000 angstroms, and all of this is deposited on silicon wafer and attacked by a neutron beam, and a grazing incidence of less than a degree, 1 degree. So colleagues, the beam has to be extremely highly collimated, and the condition here of resonance, colleagues, are given by simply by this equation. And if we do so, colleagues, we would, if the resonator is perfect with the minute, nearly zero roughness and so on, the roughness should be around the plus minus 0.5 angstrom, that is plus minus 1 atom. So it's clearly, colleagues, you would see that the quality of the resonator of the thin films is of a challenge. Anyway, colleagues, if we do that, so therefore we send in our neutron wave packet, the cold neutron wave packet, under these conditions, there will be definitely a tunneling through the first reflecting layer, and the second tunneling through the second layer, reflecting layer, and therefore we will be having a beam which will be transmitted, and the same beam will not be transmitted, which was transmitted will not be reflected. Therefore, we will have a dips in the total reflection plateau and the maximum in the transmission. And if we do so, colleagues, this is what we obtain. We have here the total reflection reflectivity profile, as you can see, and the transmitted beam, as you can see. Normally the beam, if there were no tunneling, we will be having total reflection. That means we will be observing only the total the reflection of the plateau of total reflection, which is not the case, colleagues. We see there are dips in the total reflection plateau. That means this neutron wave packet corresponding to this wavelength or to this energy have tunneled instead to be totally reflected. They have tunneled, and by tunneling they have been transmitted and therefore detected in the transmitted beam, and it's the same for this order, that one and that one and that one. So therefore, clearly, colleagues, here we show that using this extreme high quality Fabry-Perot nanoresonator, it is possible to tunnel to have the tunneling of neutron wave packets within the Fabry-Perot resonator, and to have these dips and this maxima, corresponding maxima in the total in the transmitted beam. And of course, colleagues, before tunneling twice, colleagues, the neutron wave packet has been trapped somehow, and these trapped the neutron wave packets are more or less the ones who are responsible of these resonances here. And of course, it's a tunneling. Therefore, if I use the Heisenberg uncertainty, therefore it will give me the time that the neutron wave packet which has tunneled, how much it has spent in this resonator. And doing such, colleagues, we find out that the trapping time is on the order of a picosecond and not a second, colleagues, picoseconds. So the precision, colleagues, on the trapping is in the picosecond, 10 to minus 12 seconds, and that compared somehow to the precision of the time life of the neutron by the beam and the bottle time, the bottle methodology, colleagues, you can see clearly here there we are at the second, and here we are at the picosecond. Of course, colleagues, when have to measure, when you it's quadratic type evolution, and the bar, how can I say, the bar error is really very small, and it shows clearly that this trapping of a neutron wave packet allows a high degree of precision somehow. And
Malik,
the idea,
sorry to interrupt you, Malik. We need
yes,
slowly to come to an end because we have a sharp time constraint
yes, yes,
around
yes,
5 o'clock, and we still
yes,
have a few talks. Thank you.
yes, I'm nearly done. I'm nearly done, colleagues. And here it shows clearly, colleagues, that to be able to trap neutron for a longer period, we are obliged to go to very, very large wavelengths. That means very, very low, very low, slow or cold neutrons, and that is unfortunately not using the standard neutron research reactors, but the spallation sources, and that is what we are trying to do, colleagues, with our colleagues from Russia, and to reach that point, colleagues, we are obliged to use what we call correlated resonators, and for such a resonators, coupled resonators, we are obliged to use the Zeldovich-Vinogradov approach in that regard. And I thank you, colleagues.
Very much, Malik, for the nice talk. Are there questions for Professor Maaza? Yeah, here we go.
Just for understanding, thank you for talk. And you mentioned tunneling, and I did not understand through what, through which barrier or something. What do you mean when you tell tunneling?
Let me please just, okay. Let me just go back, colleagues. Here, colleagues, normally under these conditions here of the thickness of the reflector, the transparent material and the reflector, normally in these conditions, colleagues, under this condition of grazing incidence, the neutron wave packet should have been reflected totally. But if we are in yes, if we have this condition of resonance verified, involving the angle and the thicknesses of the reflector and the transparent material, therefore the neutron will not be totally reflected, but it will tunnel through this first reflector. This is a highly reflecting material. Normally nothing would escape, all will be totally reflected.
Thank you very much, Malik, for the explanation. Are there more questions for Professor Maaza? If that, let me quickly check if there are any questions from the online participants, just in case. No, it doesn't seem to be the case. So then thank you very much again, Malik, for sharing with us some of your experiences in Lubna. And I think it